Tell me when. Hi, Brandon. We hope that you come in soon, but just in case, we are going to videotape this for you. So we're training a new videographer, so you have to bear with us. I'm sure it'll be excellent. If you would, begin, if you did not have these notes from yesterday, it didn't seem like I had much time yesterday, put them in. If they're already there, then just watch us review. So free fall, it has several parts that are required for free fall. And the first one that we require for this is that the motion has to be one-dimensional. So if you didn't have that note already, just add it to your little note-taking place there. It is straight line. And do you remember what kind of acceleration was required? I kind of added that sort of as an afterthought, but it's really important. Emily?
Gravity?
I'm sorry. In gravity, I thought your hand was off. Gravity is an example of this kind of acceleration, but what kind of acceleration did I say was required for those three equations? Yes, that? Constant, right. Constant acceleration. Remember the stink bug example? Usually when a stink bug walks across the table, he walks fast, slow. We can't use the equations for the stink bug. The constant acceleration. Now that's not constant velocity. This is constant acceleration. So keep that straight. All right, we came up with a number. See if you can fill it in before I tell you. If you've already written it, just review it. The acceleration in meters per second or feet per second squared, and feet per second squared. The acceleration due to gravity, yeah. The acceleration constant, I'll put that in. The acceleration constant. The acceleration constant is, did you write 9.8? And did you write 32? All right, we go over that, I remember. So make sure it's clearly in your notes. All right. Interesting about the acceleration due to gravity, the acceleration constant, is only true on the Earth's surface for a few kilometers above the Earth's surface. So if you're on a really tall mountain, it's actually a little bit different. So we're gonna assume that we're very near on or near the Earth's surface.
Sea level?
So 9.8. You can bring the trash can to you if you need to. You can have your own trash can. There you go. All right. Is that gravitational constant the same for a rock as it is for a feather? Yes.
Can we mistake with something? I forgot to give her money for my pizza.
What's that?
I have to give her money for my pizza.
Okay, you do need to do that, but can you just wait for a perfect pause moment? She'll take it. She'll take it. She'll call for it. She'll call for it. All right, just as soon as I get done these notes, I'll release you to do that. Yes.
Oh, to answer your question.
Yes.
It is the same for a rock or a feather, it's just air resistance.
Very good. All right, let's kind of prove that to ourselves. Is it possible, Zach, would you be the test person? Just see if you can stand on that chair since your shoes are off anyway. Be careful. All right, so physics book.
Boom!
Take your physics book
Oh, yeah.
and take your paper.
Crumple it up or not.
No, not crumple. So take your notes. All right, he's gonna hold them out. Emily, get out of the way. Pardon?
Stand on like that, if you want.
You want it hold too? All right.
Better than that
Go
one,
ahead.
probably.
Better than this thing.
Yeah.
I don't know. Go ahead.
Okay, we'll find out.
We'll find out. All right. Very good. All right. I want you to drop the paper and the book at the same time.
Oh,
That was loud.
All right. Sorry. All right. Stay there. Stay there. So
Now you drop.
Hunter's point was that it still has the same pull from gravity, the same acceleration due to gravity, but air resistance. So how could I do this a different way to remove the air resistance? Besides crumbling up your notes. I'm not going to crumble up your notes.
Yeah, put it on top of it. No, you put it on the bottom of the book.
Let's put it on the top, because that would even be a better test. What do you think? Do you think air's going to get under here?
I think a little bit might get on there.
All right, give it a try. Our hypothesis is that the book being heavier is going to remove those air molecules. So there's going to be no air resistance on the paper this time.
What about the video?
So we're expecting, if the theory is right, that it'll fall at the same time, unless some air gets under there. So give it a
Wait,
try.
this pal, hold on, I wanted to get it in the video.
Yeah. Ready?
Hey, let's do it one more time. That was awesome.
Except let's put the paper under the book.
Did Brandon see the first drop?
No, not the first
All
one.
right, do the first drop for Brandon.
See,
All
Brandon.
right.
First job is just the control.
That's better.
Is there anybody underneath of
Oh, shit.
I don't look.
Oh, can we tell?
this?
Oh, I thought
Okay.
it was
Brandon,
going
we were
on top.
seeing,
Yeah.
showing you that the paper was, even though the same acceleration constant was for both, the paper experienced air
That was 1 feet,
resistance.
apparently.
All right.
Can we try doing it with the paper on the bottom of the book?
Well,
I don't know how I could get, I don't know how that would, how the paper would ever get out of the way of the
No,
book.
no, on the bottom of the book. Flip
We
it
can
over.
try it, but do this first.
Okay.
Yeah, it hit exactly the same time. No air resistance there. All right, just for some point, which I don't understand, we're gonna try.
Just
try.
like that.
All right, go ahead.
I'll be able to see it.
Okay. All right, thank you, Zach. That was awesome.
If no other reason than to flatten out the paper.
Yeah. Now we know what to do if you got a wrinkled paper. All right. So let's take a note here then. Is it the same for a rock or a feather? Yes. The answer is the acceleration due to gravity is the same for a rock or a feather.
Doesn't gravity
So the
have-
experiment was what Zach did. So let's do a problem. Are we
Does
going to
gravity
say?
have more of a pull on something depending on how great the mass is?
The force is, because we'll learn that force equals mass times acceleration. But the acceleration on that object is the same.
Oh, I see.
Okay. All right. Let's go ahead then. Oh yeah, we were supposed to time this. Don't even figure out how long have we been going. I always forget.
Probably like 10.
How much
10
of
minutes.
class time are we
Probably
doing?
like 7.
All right, we'll go like 3 more minutes and then close it down. So let me get to that. So when it gets to 3 minutes, we'll have to shut it down and start part 2.
When it was like, I'm awesome.
All right, let's draw an example of an object in free fall. So you get to pick the object, draw a person on a cliff. The cliff is 0.150 kilometers high, and the person is dropping something. Mine is a penny. So you can be more creative than that. See what your person is dropping. Go ahead, draw the picture.
That's too big to be a penny.
Sorry. My artistic, it's part of my artistic license. Dropping something off the cliff. Pick something. Pick something. It's kind of hard to get the air resistance out of the picture. Pick something that will not be influenced by air resistance.
I'm recreating Star Wars over here.
Yeah,
Alright, what are you dropping there, Emily?
I don't know. She was dropping a body.
Bouncy ball.
Drop loop.
No, why not?
Drop
Drop break. How
Oh,
about
you can
drop break?
Oh,
You can
from
turn
six.
over and draw in the back when you run out.
Yeah, definitely from
I'm
6
dropping my physics textbook down
Yes, Rick is great.
over the.
Five.
Oh.
No, it's like to be a
Off the
small.
six.
I'm dropping a penny.
I'm
My
dropping my
mom
physics
used
book.
to say, do you ever see a penny on the ground and not pick it up?
Yeah,
That's what I thought.
Yeah.
Did you ever see a penny on the ground and not pick it up?
yeah.
Well, my mom said, she said, he who will not save a penny will never have many, or something like that.
One time I almost
So
left
when
a
this
$5
gets
bill
down
in
to the
the
bottom, I'm picking it up. All right, you got your sketch? Let's look
Well, you gotta
at,
wait for it to load.
how many minutes are we at, Emily? Martin?
how many minutes are we
2.
2, okay. All right. What we're gonna do is use our old, the same old kinematic equations, the the voting and the axing and the attaching, those three. So we're going to do the same thing to figure out what equation to use. And the question is, did you write the question? Find the velocity at the ground. So you might say 0. Find v at the ground. I don't mean when it's on the ground, obviously that would be 0, but the instant before it touches the ground, what is its final velocity? So write down the question, final velocity, and remember our symbol is v now for the final velocity. Alright, so let's do our list. V, X, A, T, V sub O, and 1, 2, 3, 4, 5. That's all of them. Oh wait, do we have to shut down?
Yeah.
Okay, Brandon, we'll pick it up on part 2. Go ahead.